Welcome back, friends. Gotta come here. Welcome back. So, section 4.6 in Venema's Foundation of Geometry deals with the thing we have yet to discuss. What happens if the figure has four sides? What happens if you've got a quadrilateral? Now, so we're clear, when we're talking about quadrilateral ABCD, we mean that there are four line segments, AB, BC, CD, and DA. They share no more than an endpoint. No two segments share more than an endpoint. So you've got quadrilateral A, B, C, D. They're named in order, either clockwise or counterclockwise. You could talk about opposite sides. BC is an opposite side to AD. CD is opposite to AB. We could talk about the diagonals. The diagonals would be the line segments AC and BD. We should also recognize that order matters. If we were to talk about ABCD, that would be different than talking about ACBD. In fact, you might recognize that ACBD is not much of a quadrilateral at all because the segments AC and BD share more than an endpoint. Very well. Let us undo. Great. When we talk about the sum of the angle measures for a quadrilateral ABCD, we only define that for convex quadrilaterals. And you may ask the question, why do we only define that for convex quadrilaterals? Why can't I talk about A, B, C, D? Maybe A, B, C, D. Why can't I talk about the sum of the angle measures? And the answer boils down to, give you a moment to think about it, the angle measure here. Remember, we did not define angle measures bigger than 180 degrees, so that's a problem because that angle right there is what you might have learned in high school as a reflex angle, something greater than 180 degrees. So that's a problem. We do not therefore define the sum of the angle measures of a quadrilateral for non-convex quadrilaterals. It's just not interesting to us. But in a convex quadrilateral, guess what? In a convex quadrilateral ABCD, the sum of the angle measures is less than or equal to 360 degrees. This will actually be something that you will consider when we get to class. You will actually prove this. And it's not that hard. It's really just one line segment that we add to the picture. I think with one line segment added to that picture, you can prove it. Okay. Theorem. Every parallelogram, every one is a convex quadrilateral. Every one. So let's see if I've got a parallelogram. I probably don't. It would be too much to ask for a parallelogram, so I'll make one. This will be parallelogram. Oh, terrible. Sorry, folks at home. That's embarrassing. This is parallelogram ABCD, and by parallelogram, we mean that both pairs of opposite sides are parallel. Line segment AB is parallel to line segment CD. Line segment AD is parallel to line segment BC. And in fact, the lines containing those segments are parallel. So every parallelogram is a convex quadrilateral. Here's what I'm going to do. Without loss of generality, I'm going to show that C is in the interior of angle DAB. I'll show C is in the interior of angle DAB without loss of generality. And if I can show that C is in the interior of its opposite angle, then I can show that any of the vertices is in the interior of its opposite angle, and then we have a convex quadrilateral. So I'm going to argue, since DC is parallel to AB, that's definition of parallelogram, then D and C are on the same side of AB. Now that's important because the interior of angle DAB is on one particular side of AB. Similarly, since BC is parallel to AD, B and C are on the same side of AD. So that matters for the following reason. D and C are on this side of AB. B and C are on this side of AD. So when we look at the interior of angle DAB, it's the intersection of those regions, which happens to be where C lies. C lies in the interior of both. It lies in the interior of the angle because it lies on the same side, on the correct side of both rays. So C is in the interior of angle DAB, and similarly for the others. It's a simple argument to make. Every parallelogram is convex. Not hard at all. Slightly more difficult, and also yours to prove when we get to class. If ABC is a triangle, so I've got triangle ABC, and D is somewhere between A and B, and E is somewhere between A and C, then quadrilateral BCED is convex. BCED is convex. This will be yours to finish up. I think you'll be able to do it with a similar argument to the one I just did. Two things are obvious here. One is that D has to be in the interior of angle BCA because D is between A and B. And here's the interior, so D lying between A and B must fall in the interior of angle BCA. Similarly, E is in the interior of its opposite angle because E is trapped between A and C, and here's the interior. So with E trapped between A and C, it is in the interior of angle ABC. It will be your job to argue that B is in the interior of angle DEC and C is in the interior of angle BDE. But I think you can make some good same side arguments and nail that sucker down. Speaking of convex, ABCD is convex if and only if AC intersect BD, and by that we mean segments. Segment AC intersect segment BD is non-empty. And if I can go back to the original, AC intersect BD is non-empty. But AC intersect BD is very empty. So it appears to make sense that ABCD is convex if and only if AC intersect BD is non-empty. And then if ABCD and ACBD are both quadrilaterals, then ABCD is not convex. And the argument goes the same way. If I had, no, let's do it this way. Let's not be crazy. If I have A, B, C, and D, and I connect them A, B, C, D, that's a quadrilateral. And I connect them A, C, B, D. What the heck is that? That's not a quadrilateral. ABCD is convex, but if I play the game just a bit differently, A, B, C, D, and ACBD. Those are both quadrilaterals. And since those are both quadrilaterals, then ABCD is not convex. Not. In fact, neither is ACBD. That's just obvious. Okay, so far so good. We are on our way through quadrilaterals. Neat.